This should be fun. All right, so let's get into thermo stuff. All right, so last time we talked about the effect of the boiler and condenser pressure on performance, and talked about how if you up the pressure in the boiler or lower the pressure in the condenser, both of those will improve performance because of what they do to the temperature. We compared our ideal Rankine cycle to the Carnot cycle and showed that they're not the same. The Rankine cycle has the heating occurring at constant pressure, whereas the Carnot cycle has it occurring at constant temperature, so slightly different. And then we talked about some principal irreversibilities and losses and pointed out that the primary ones that we're concerned about internal to the Rankine cycle are isentropic efficiency of the turbine and the pumps, turbines and pumps, if there's more than one, which we'll get to that today. And so we set up an example, and so we're going to finish it. That's the first thing today. And then the next thing we'll talk about is one method to improve performance, which is called Superheat and Reheat. And then maybe if we get to it, we'll talk about regeneration, which is another method. On your homework, you only need to worry about Superheat and Reheat. So if we don't get to regeneration, it doesn't hurt. I think there's only one, like the last question in your homework, I think, is about Superheat and Reheat. Okay, so let's go ahead and get into it here. Okay, so we'd set up this example where we had the same Rankine cycles we had before in the ideal case, except that this time we have isentropic efficiency of the turbine and the pump at 85% each. And so our TS diagram actually looks like this now. We noted that H1 and H3 are the same as in the previous example, so I just wrote those down. And then our H2 and H4 from the previous example become H2S and H4S, okay? But we actually need H2 and H4 for this problem. So the way that we're going to do that is simply by using the definition of the isentropic efficiencies. So let's do the turbine first. So A to T is defined as H1 minus H2 over H1 minus H2S. I can solve this for H2, and I get H2 equals H1 minus A to T times H1 minus H2S. I have all these numbers now, so I can just plug in and solve for H2. So H2 is going to be, it's 2758.7 minus 0.85 times 2758.7 minus 1795.1. And this is all in kilojoules per kilogram. Put this into your calculator and you'll get the H2 is 1939.6 kilojoules per kilogram. Okay, and now we have to get H4 from the definition of efficiency for a pump. So A to P is equal to, in this case, H4S minus H3 over H4 minus H3. Again, I can solve for H4. That's the one that I want. So H4 equals H3 plus H4S minus H3 over A to P. I have all the numbers again, so I can just plug those in. H3 is 173.84 plus H4S was 181.89 minus 173.84 divided by the efficiency, which is 0.85. Again, this is in kilojoules per kilogram. Put this into my calculator and you get H4 equals 183.31 kilojoules per kilogram. Okay, and so now, just like we did before, we can use these enthalpies at the various states to figure out what our parameters are that we want to know. So part A, the first thing we want to know is the overall thermal efficiency. So this we saw from before, we derived for a Rankine cycle is equal to 1 minus H2 minus H3. That's Q out divided by H1 minus H4. That's Q in. Okay, I have all the numbers again, so this is 1 minus, so it's 1939.6 minus 173.84 divided by 2758.7 minus 183.31 is what I have. Is that the right number? Yeah, 31. And the units are going to cancel, so I won't bother writing them down. And so I get the overall thermal efficiency is now 31.4%. And just as a point of reference, if you flip back, the efficiency for the ideal cycle was 37%. Okay, so you can see what the effect of the isentropic efficiencies has on the overall thermal efficiency, right? It lowers it as sort of as what we expect. Yeah, so a question about what is H2S versus H2, or equivalently H4S versus H4. So again, this is when you go through a turbine or a pump that has an isentropic efficiency associated with it that's different than 1, that's less than 1. H2S, or state 2S really, this is the enthalpy at state 2S. State 2S is a virtual state that you would have at the exit of the turbine if the turbine were isentropic and had the same exit pressure as it actually does. So the state 2S does not exist in reality. It's a virtual state that would exist if the turbine were isentropic. So it has the same entropy as state 1, and then we specify the exit pressure. Okay, and then state 2 is the real state where the entropy is increased through the turbine because it's irreversible. Similarly with state 4 and 4S, 4S is a virtual state that doesn't exist. It's if the pump were isentropic. So we specify the exit pressure. It has the same exit pressure as the real state 4, the real exit state, but it's isentropic from the inlet. So it has the same entropy as state 3. Okay, so it's a vertical line on a TS diagram. And state 4 is the real state where the entropy is increased. Okay. You can go back and check out the video or the notes from when we derived isentropic efficiencies for devices in the last chapter if you need a little bit more clarification on that. Okay, isentropic efficiency is a really important topic, and we're going to continue to use it for the rest of the course. So make sure you understand it. Okay, make sure you understand how to do these calculations. All right, part B is the back work ratio, or BWR. This is defined as H4 minus H3 over H1 minus H2. I won't go through the pain of putting in each individual number. We have all the numbers. You can plug them in. You'll get this is 1.16%. And the back work ratio for the ideal engine, or sorry, ideal cycle was 0.84%. So the back work ratio has gone up, which means the ratio of the power that we have to put into the pump compared to the power we get out of the turbine has gone up. Okay, usually you want this to be small. So the isentropic efficiencies are hurting this as well. Mass flow rate for the steam. Remember, we got this from before, from looking at the net power of the cycle divided by the enthalpy differences. So this is the power out from the turbine per unit mass, and then minus the power into the pump per unit mass. You can look at the example from last time to see sort of like how this is all spelled out. But again, I have all these numbers. The net power for the cycle was again 100 megawatts. And so again, I won't plug in all the numbers explicitly for you. I'll just write down the answer. This comes out to be 123.5 kilograms per second. And then just to remind us, the ideal mass flow rate for the steam or the working fluid was 104.7 kilograms per second. So basically, to get the same amount of power, you have to pump more steam through your cycle to get the same net power output because your efficiency is lower. Okay, these things all kind of go together. Heat into the boiler. This was m dot s times H1 minus H4. Again, we have all these numbers now. This comes out to be 318.1 megawatts. And the ideal Q dot in was 269.8 megawatts. So we're pumping in way more energy into the boiler in order to get the same amount of power output. This is just a consequence of having lower efficiency. Likewise, Q dot out was M dot S times H2 minus H3. This is the heat that goes out through the condenser. I have all these numbers again, so the answer comes out to be 218.1 megawatts, and the ideal was 169.75 megawatts. So this one might be less obvious as to why this goes up. If you look at the equations for like the overall thermal efficiency, you'll see why that is. You kind of have to puzzle through it a little bit. But what this means is because the cycle is less efficient, and remember, I didn't do anything to the condenser or the boiler directly. I just changed the isentropic efficiency of the turbine and the pump. But because of that, I now have to put in, or sorry, I now have to get rid of way more waste heat than I did before. Okay, so it's a lot more expensive to get rid of the waste heat because of the inefficiencies. So really, the inefficiencies cause everything to be worse, right? Our overall efficiency goes down, work ratio goes up, goes up. We need more steam going through the system to get the same power output. We need to put in a lot more heat, and we have to dissipate a lot more waste heat. Okay, and then finally, the mass flow rate of the cooling water. Right from the previous time we solved this problem, we showed that this was equal to the heat transfer going out times the specific heat of water, C, times the change in temperature of the cooling water from the inlet to the outlet. And so this comes out to be 2.61 times 10 to the 3 kilograms per second, or 2.61 metric tons per second, right? And then the ideal mass flow rate of the cooling water, or the mass flow rate of the cooling water for the ideal system is probably a better way to say that, was 2.03 times 10 to the 3 kilograms per second, right? So we now have to pump. I mean, it makes sense, right? Because Q out has gone up. We have to pump a lot more cooling water now through our system to get rid of the waste heat. All right, so that's that example. You can kind of see the effect of the isentropic efficiency of the turbine and the pump on all the overall performance metrics. So now let's talk about how we would improve performance.
No, because I was out.
There's a couple of ways we can do this. The first way we'll look at today is called Superheat.
I can't think of anything right now.
And Reheat, which are two different but related
just an update.
Methods.
There's a minor one. I've been working to get input regarding training.
So
I talked to the DMU.
Our ideal TS diagram, just to remind ourselves, looks something like this. So I'm going to put state 1 way up here because we've increased the boiler pressure a lot. Come down to state 2S. Come across to state 3. Up to state 4S. I'm going to use 2S and 4S now because I'm showing the ideal cycle. So just to differentiate between a real cycle and an ideal cycle. And then straight across to close the system. So we saw before that increasing P1, the boiler pressure, boosts efficiency.
Know that we will be able to schedule training and let people sign up for this classes.
But it also reduces quality at the turbine exit. Okay, so you can see that because of the slope of the saturation curve, right? If I lower the pressure, then state 1 sort of moves to the right here. And so when you come down to the same exit pressure, your state 2 or 2S is going to have a higher quality. It's going to be closer to being vapor. But as you increase that to boost your efficiency, this state 2 or 2S is now moving to the left, which means the quality is decreasing for the same exit pressure. I've alluded to this before, but this turns out to be bad. Having low quality at the turbine exit. So low quality at the turbine exit creates droplets. So liquid water droplets, right? Because you're in a two-phase region, so you have some vapor and some liquid droplets. and these droplets hit the turbine blades.
I don't think we're going to get
which erodes them.
at the end of
The more droplets you have, the worse the problem is. Okay. The other thing is that turbines don't work as well with, so if you have a turbine designed for vapor, it doesn't work as well on a liquid in terms of extracting enthalpy. So actually the isentropic efficiency will be lower if it has to process too much saturated liquid. So you have both this erosion problem and a reduced efficiency problem if the quality is low. So our common practice
sets up before we actually finish the
for steam
process. So,
turbines
like, this is not gonna be
is
like a
to
project
keep
goes out like we usually do, right?
X2 greater than about 90%. That helps to
Okay.
kind of alleviate this issue.
Uh-huh.
So how do we achieve this, right? Because we want to get good efficiency. So you want to push this up, but that's going to reduce your quality. So how do we pull this off? We achieve this.
Yeah. Okay.
And actually, we also get better efficiency.
Okay. So it's going to be you, Scott, Nick, myself.
As a side effect through Superheat.
Okay. All right.
And Reheat. So we'll talk about Superheat first, and then I'll show you what Reheat is.
About,
So in Superheat,
talking about our favorite customer.
your TS diagram now looks like this.
He's chirping again.
Okay. So instead of being here at a saturated, here as a saturated vapor, we'll actually heat. So if we start at state 4S here, we heat along here at constant pressure, right? We hit saturation, we come straight across. And then instead of stopping, we just keep adding heat. It's still at constant pressure, but now the pressure is going to go up because we follow that isobar. So we actually heat all the way out to say state 1. Okay. And this part of it is what's called the superheat. We call it superheating because you create a superheated vapor. Get it? Superheated vapor, superheat. See how that works together? And so now when this drops down to state, the way I've drawn it, actually, we're sort of like sitting in the, oh wait, sorry. Let's go down a little further. My bad. Let's go down to here. So there's 2S. So now instead of being over here, 2S is now over here because we've heated it more. Okay, so it helps get our quality higher at the exit of the turbine. Okay, and then we still come across to state 3, and gosh, I screwed this up. It's supposed to be a vertical line to state 4S. I'm just gonna make that dot bigger so it looks better. There you go. Okay, so that's what the diagram is gonna look like now. Okay, so I said it makes it more efficient. Why is that? Well, now the average temperature in the boiler is higher. So just like we said, raising the pressure, the reason why it improves the efficiency is because it increases the temperature in the boiler. Well, likewise, this is also going to increase the average temperature in the boiler. It's going to boost it up a little bit because you have now this little kick at the end that has a higher temperature than when we were going across the phase change. Okay, and so we get 2 benefits out of this. The overall efficiency goes up, and the quality at the turbine exit goes up. It's a win-win. So we like superheating. Okay, this also changes the terminology a little bit. So instead of boiler, a lot of times we'll use the term steam generator because strictly speaking, we're not just boiling the water anymore. We're now superheating the water vapor. So we'll call it a steam generator because really that's the goal, is to generate steam at high temperature and pressure. Okay. So steam generator, boiler, they mean the same thing. We just call it a steam generator because it's doing more than just boiling the water. All right. Reheat is another strategy to boost X2. It doesn't really help with efficiency, but it can help us boost X2. So what that would look like, and we'll refer to this diagram, we're going to do an example in a second, so we'll refer to this diagram for the example. There's our saturation curve. All right, let's see, where do I start? Diagrammers, they're getting more complicated. They're going to get even worse as we go along. Not worse, more exciting. Let's say more exciting. They're going to continue to get more and more complicated. That's what I'm trying to say. All right, so we'll put state 1 over here, so we'll do some superheating. Okay, and then we'll come down to state 2, except instead of going all the way down to our low pressure and getting into a quality that might be less than 90%, I'm sorry, my fist is blocking this. Instead of getting all the way down to something that might be less than a quality of 90%, before we get there, what we'll do is we'll pipe it back into the steam generator. I'm going to draw you a diagram in a second so you see how this works. And heat it up again. So this will be state 2. This will be state 3. And now we'll run it through another stage of the turbine and come down to state 4. So you can see we're basically extracting the same amount of power in the end, right? Because we have to pay for it by putting in more heat. So it's not like we're getting more power out, but we're avoiding the issue of running two-phase mixture through a turbine. We're basically trying to keep the quality on the right side of the saturation curve. We're trying to keep those turbine states on the right. That's what we're doing with reheat. Okay. And then once we get to state 4, we'll come across through our condenser to state 5. So we just have to increase the number of states that we have. So this now becomes state 5. And then we go through our pump right up there to state 6. This goes across here and then up like that. All right, so that's what our cycle with reheat. So I'm going to write that.
Okay, I'll just let him know and I'll CC you in. So I'm like, hey, Mandy, I'm going to just connect you to Karen right away.
Okay, so that's what our cycle would look like with superheat and reheat.
Okay.
The diagram is going to look something like this. So we have our boiler here, which we'll now call a steam generator.
But that's over marine right now.
Okay, we still have our state 1 coming out of the steam generator, going to a turbine. Turbine 1, okay? Now this turbine is connected via shaft to turbine 2. Okay, the steam after it comes out of turbine 1 actually gets piped back into the steam generator. Okay, and so there's state 2 somewhere here. We run it back through the steam generator. After it comes out of the steam generator again, we're at state 3 now. We've heated it up. And then we come back in here and go into the inlet of turbine number 2. Here is where we extract our power, which is sort of like the combined power of the 2 turbines. And then out of the second turbine comes state 4. We run that into our condenser. Right, I guess we have heat going into our steam generator. We run this out of the condenser. It comes out of the condenser at state 5. We put it through our pump by supplying power input. We come out of the pump at state 6, and then we go into the steam generator. Okay, so that's what our diagram now looks like for superheat. Superheat doesn't change what the actual like plumbing diagram looks like, but reheat does. So we split up our turbine into 2 stages, and in between the stages, we run the steam back into the steam generator to get it heated back up again. Okay, so that's how the diagram changes and what it looks like. Okay, so now that we've seen that, question? Or was that an inadvertent unmute? Okay, so let's do an example of this now, which will help you with your homework. So we'll do power plant with the same high, which would be 8 megapascal, and low, which would be 8 kilopascal pressures as the first example where we just had the ideal cycle, but with superheat and reheat. And we'll do it with an ideal cycle. So, I mean, obviously, as the systems get more complicated, you can have more fun. So I could have this turbine have an isentropic efficiency. I could specify an isentropic efficiency for this one, and they could be different. I could also specify an isentropic efficiency for this pump, and they could all be different. And we could have lots of fun going through the whole example. But because this is just an example in class, I'm not going to do that. Okay, we'll just do ideal. Everything's ideal, everything's isentropic, so we won't have to deal with the isentropic efficiencies. So let me give you some data for our plant. So state 1, the pressure again is 8 megapascal. And the temperature now, instead of being the saturated vapor temperature, is going to be 480 C because we've superheated the steam. State 2, P2, is 700 kPa. So this is the pressure in between the turbines. And then state 3, the piece of information I'll give you there is that T3, which is the temperature going into the second stage. So really, when you set up these complex Rankine cycles, the data you need are the input states to the turbines, right? I'm giving you P1 and T1, and P2 and P3 are the same, which we'll show later on. So I'm being a little sneaky and telling you it's P2, but really it's also P3. And then T3 is 440 degrees C. Then at state 4, you need the pressure at the bottom. So you need the pressure down here. I'm actually going to kind of, maybe not, never mind. Sorry, P4 equals 8 kPa. State 5, I'll tell you, is a saturated liquid. And the other piece is that the net power is still 100 megawatts. Okay, so this turbine work is the combined, or turbine power is the combined power of both turbines together. So we're going to find the overall thermal efficiency for the cycle, the mass flow rate of the steam, and the waste heat generated that comes out of the condenser. All right, so our system has gotten much more complex, but really the solution strategy stays the same. What we're going to need for these is the enthalpy at every state. That's what you need whenever you solve one of these problems, whether it's a Brayton cycle problem that we'll do in next chapter, a Rankine cycle problem, no matter how complicated the system is, or a refrigeration cycle problem, which we'll do 2 chapters from now. In all of those problems, what you need is the enthalpy at every state. That's what you need to solve the problem, to get, whatever I ask you for. Okay, so that should be your first thing, and all you got to do, doesn't matter how many states there are. Eventually, we're going to get to Rankine cycles that have like 12 states because they've got regeneration cycles and all kinds of stuff. And in your project, you'll design ones that have really complicated diagrams that have lots of states. The strategy is always the same. Start at a state where you know what the state is. State 1's usually a good place to start. And then just systematically work your way through the system and find the enthalpy at all the states. Okay, and then once you have those, it's just a matter of putting them together into some algebraic expressions to get the power and the efficiency and yada, yada, yada. Okay. All right, so let's do state 1 first. I have T1, well, I have P1 and T1. That's enough to get the state. So the enthalpy at state 1, I calculate to be 33. I don't calculate. I put it into RefProp, and RefProp does the calculation for me. 3349.6 kilojoules per kilogram. Moving right along, let's do state 2. Okay, so there's a question. This is a great question. Why do these systems pump out so much heat in the condenser when it just superheats it back up again right after? That's a great question. Okay, let's think about this. We have to pump out a ton of heat here, and then we have to add heat back in here. Why do we do that? Why do we have to do that? There's a couple sort of naive things that I can tell you that would explain why we have to pump out heat in the first place. One is that one of the definitions of the second law is you can't have a power cycle operating between two reservoirs where the only thing you do is take in heat and put out power. You have to have waste heat rejection, otherwise you violate the second law. That's one of the things. So that explains why we have to have heat rejection to begin with. Number 2 is another consequence of the second law is that you can't have heat flow from cold to hot. So the temperature that we have down here is colder than the temperature here. So this heat that's flowing out, I can't flow this heat to state 6 to heat it up because this is at a lower temperature than this is. The heat won't flow that way. It won't do it. That would violate the second law. So the second law is killing us, right? If only there were no second law, we'd be able to have free energy forever. But because of the second law, there's two things, those are two things that we just can't do. Now, the reason why I said this is a great question is because the very next thing we're going to do after we do this example is regeneration. And regeneration is exactly what you're referring to here, which is taking some of this thermal energy that's left over in here and using it to preheat the stuff going into the steam generator so that we don't have to provide so much Q in. Okay, and it's another way to boost the efficiency. So that's coming. We're going to do that. That's like the last big improvement that we can make to these systems, okay, to make them more efficient. All right. So state 2, we're given P2. The other relationship that we need, if we come back here to our diagram, we can see it, is that because this, sorry, I didn't even label my axes. What am I doing here? This is entropy. And so because we have an ideal turbine, if you had a non-isentropic turbine, you would still follow the same procedure. You'd find state 2s, which is the virtual state at constant entropy, and then use your efficiency to find the real state 2. But in this case, we don't need to do that. So the conserved property is entropy. That's the other one that we know. So S2 equals S1. Well, I didn't have S1, but I can get it. I could just go back to my chart from RefProp and see that S1 is 6.6613 kilojoules per kilogram Kelvin. Okay, so using that, I now have the entropy and the pressure. That's enough to specify to pin the state, and so that gives me H2 is 2742.7 kilojoules per kilogram. As a check, I should verify that the quality is higher than 90%. This is something you'll need to do in your project. So I should just confirm that. And if I look at what the quality is, I'll see that it's 99%. So we're good. State 3. The heating occurs at constant pressure. So P3 equals P2, which I have. And I'm told T3 is 440 Celsius. So again, I have pressure and I have temperature. I have two properties, and so I can pin the state. H3 is 3353.9 kilojoules per kilogram. To get from 3 to 4, I'm going to go through another turbine. And so just like I did before, I'm going to need the entropy. So I'm going to write that down just in anticipation of needing it. 7.759 kilojoules per kilogram Kelvin. State 4, I'm given P4. I have that, right? That's 8 kPa. And because I have an ideal turbine, S4 equals S3. So I have pressure and I have entropy. So now I can get that H4 is 2428.8 kilojoules per kilogram. And again, I'm at a turbine exit, so I should just verify that the quality is high. The quality here is 93.9%. So again, I'm 2 decimal points, 0.939 or 93.9%. So yes, we're good. We have higher than 90% quality there. State 5, we're told that it's a saturated liquid, which would be a quality of 0. That's one of our properties. And we know that this condensation occurs at constant pressure, so P5 equals P4. That tells us that H5 is 173.84 kilojoules per kilogram. I actually didn't write down what the entropy was. Oops. We'll need the entropy because we're going to go through a pump. So maybe look that up on your own if you want to rework this example. State 6, we know that P6 equals P1 because we're back going into the steam generator, and that occurs at constant pressure. And S6 equals S5. So I have pressure and entropy. That's enough to get the enthalpy, which is 181.89 kilojoules per kilogram. Great. So now that I have the enthalpy at every state, I can answer my questions. So part A, eta equals, there's different ways you could write this, but in the end, you'll get equivalent expressions. I'm going to write this as the net work output divided by the heat input. Now we need to be careful here because now we're doing superheat. Well, superheat doesn't change anything. We're doing reheat. So we have 2 turbine stages and we're also heating it twice. Okay, so there's 2 Q-ins now. So this is the power from the first turbine plus the power output from the second turbine. That's our total power output minus the power input to the pump. Later on, we'll have systems that have multiple pumps, and you could have 3 or 4 turbine stages. You could have lots of reheats. So when you have this, right, you have to account for every turbine stage and every pump that you have in your system. And then we have Q for the initial heat from state 6 to state 1. And then we also have a heat input now for the reheat from state 2 to state 3. So again, if we have multiple reheats, you have to account for every time you add heat to the system. That all goes into the efficiency. Okay. Now I can write these all out in terms of the enthalpies, which I've done before, but I'll do it again just so that we can see it. So the power to turbine 1 divided by the mass flow rate of the steam is H1 minus H2. The power to turbine 2 divided by the mass flow rate of the steam is H3 minus H4. Enthalpy at the inlet to that turbine minus the enthalpy at the outlet to that turbine. The power going into the pump divided by the mass flow rate of the steam. And I've defined each one of these so that the powers and heats are all positive. That's why I have a minus sign here, so that everything comes out to be positive. So for this to come out to be positive, this has to be H6, which is the enthalpy at the exit to the pump, minus H5, the enthalpy at the inlet. The heat transfer in for the heat step is H1 minus H6. Enthalpy at the inlet minus, enthalpy at the outlet minus enthalpy at the inlet. And likewise for the reheat, it's the enthalpy at the outlet, which in this case is H3, minus the enthalpy for the inlet, which is H2. All right, so now the efficiency formula is going to get a little bit longer because we have all these different ingredients now. So I'm going to plug these expressions into here. The m dot s will cancel out. And so eta turns out to be H1 minus H2 plus H3 minus H4 minus H6 plus H5 divided by H1 minus H6 plus H3 minus H2. Nice, big, complicated expression. Okay, and by the way, if you defined eta as Q in minus Q out over Q in, or 1 minus Q out over Q in, and then you came up with what the enthalpy expression for Q out is, which I think in this case is fairly simple. It's just H4 minus H5. You would wind up with the same expression. The algebra would work out such that you get the same expression here. And so this works out to be 40.3%. Actually, your formula might be a little simpler because you could probably do a little bit of algebra. You could like factor out, there's an H1 minus H6 plus H3 minus H2 here in the numerator. So you could like factor that out. And so you get 1 minus H5 minus H4 over this. So maybe a little cleaner that way, but whatever. I did it this way. And so without superheat or reheat, our efficiency was 37.1%. Okay, so we've boosted our efficiency by a little over 3%. This may seem inconsequential, but when you're running a power plant for 20 years, you know, even a 1% change in the efficiency is an enormous benefit. So you'll find, I mean, when you go to industry or whatever, that wherever you end up, that folks doing power plants or engines for cars or engines for airplanes, I mean, they fight for fractions of a percent improvement in efficiency, because over time, those translate to significant savings in money or emissions or whatever it is that, you know, whatever the bad thing is that you're trying to minimize. Sometimes it's both. If you can minimize both, then hey, you know, win-win, right? Okay, so there's our efficiency. Part B, we can use the total energy balance to get the mass flow rate of the steam going through. So the net power is the power coming out of the first turbine plus the power coming out of the second turbine minus the power going into the pump. And this is going to be the mass flow rate of the steam times, and this big long differences in enthalpies, H1 minus H2 plus H3 minus H4, minus H6 plus H5. I can solve this for m dot s. This is like what I did before. It's just more numbers. So it's the net power, which I was told is 100 megawatts, divided by this long string of enthalpies, H1 minus H2 plus H3 minus H4 plus H6 minus H5. Wait a second. I have a sign wrong somewhere. This should be a minus, and this should be a plus. And so this comes out to be 65.6 kilograms per second. This is the right answer. This was just wrong. And before, so without superheat and reheat, it was 104.7 kilograms per second in our ideal cycle before. Okay, so we've cut this down substantially. This is the amount of steam you have to pump through your system. This means smaller pipes, which means they're less expensive. Okay, so this is a significant improvement as well, right? Because this is your startup costs and also your maintenance for costs. If you ever have to replace a section of pipe, your pipes are smaller. Finally, Q dot out is just m dot s times H4 minus H5. I have these numbers, so this comes out to be 148 megawatts. And before, in our first example, the ideal cycle with no superheat or reheat, this number was 169.75 megawatts. Okay, so this is, we have less waste heat rejected, which means we need less cooling water, okay, which is also a benefit, right? Smaller pipes, if you're pumping your cooling water actively, that means your pump doesn't have to work as hard, so it's less expensive to operate. So all good things are happening because we've added superheat and reheat. So just to close this discussion of superheat and reheat, of course, in reality, all the processes in the turbines and the pump generate some entropy. They're not isentropic. And so the real performance is poorer. So just like we saw going from the ideal Rankine cycle to a cycle where the turbine and the pump had isentropic efficiencies of 85%, we saw the performance degrade. If you did this again to here, you would see the performance degrade again. But it would be much better than it was without the superheat and reheat that we saw in the first example we worked today. Okay, I think what I'm going to do is I'm just going to start drawing the picture for regeneration, just so that we can introduce it today. Maybe I won't even draw the picture. Maybe we'll just talk about it. So another idea to increase performance is regeneration. And so this is going to get back to Sam's question about why are we wasting so much heat when we have to put heat input. So regeneration, I'll abbreviate it regen, uses some of the heated fluid to preheat the feed water. Remember, the feed water is the water that goes into the steam generator. Okay, and so this reduces the necessary Q dot in. So I'm going to draw a schematic for this, and then we'll do the, I'll draw the TS diagram on Monday, okay, just so that you can kind of see how this works. I'm going to draw it on a new sheet of paper because I don't have space. This will be a big diagram. Okay, so we have our steam generator, SG. We got heat going into it. Come out of here at state 1. We go to a turbine, T1. This turbine is connected to a second turbine. This looks like it did for reheat, except this time we're not going to reheat. We are going to split this up, however. We're going to have a state 2 come off here. Okay, and we're going to have a fraction of the water, Y, go this way on this path. Okay, we're going to have power coming out of both stages of the turbine. We're going to come out here to state 3 and divert the rest of it, which is 1 minus Y, into a condenser, which is going to pass waste heat out to the environment. This is going to get to state 4. We're going to run this into a pump, our first pump, which is going to pump it up to state 5, pressure 5. And in this case, we're going to use something called an open feed water heater. So in an open feed water heater, all the streams coming in have the same pressure. Okay, it's just sort of like a big open tank, and we're just going to mix everything together. So they all have to be the same pressure. That's why we need this pump, is to kick the pressure from state 4 up to state 5 to equal the pressure coming out of that first turbine stage at state 2. They're going to mix together, and they're going to come out of here at state 6, and recombine. They're going to go into a second pump. So each of these pumps has its own work input, or power input, P1 and P2. And then that's going to go now to state 7 and go back into the steam generator. Okay, so that's what this system is going to look like. We're going to divert some fraction of this Y away from the second turbine. So it all goes through the first turbine, but only part of it goes through the second turbine. And the part that doesn't go through, we're going to pass into this feed water heater to help us alleviate some of this heat in load that we need to put on here. Okay, so we'll draw a diagram for this and work an example on Monday. Until then, everybody have a nice weekend, and I'll see you Monday.
Thank you.